This is Lauren Mitros. Today I'll be solving Heat Transfer Problem 8.7 from the 8th edition of Fundamentals of Heat and Mass Transfer by Bergman and Levine. So, problem 8.7 states, consider pressurized water, engine oil, unused, and NaK 22% to 78% flowing through a 20 millimeter diameter tube. Determine the mean velocity, the hydrodynamic entry length, and the thermal entry length for each of the fluids when the temperature is 366 Kelvin and the flow rate is 0.01 kilograms per second. Also determine the mass flow rate, the hydrodynamic entry length, and the thermal entry length for water and engine oil at 300 and 400 Kelvin and a mean velocity of 0.02 meters per second. So first, we will write down all of our givens. We have pressurized water, unused engine oil, and sodium potassium of 22% to 78%. The diameter of the pipe is 20 millimeters, and part A tells us that the temperature is 366 Kelvin, and the mass flow rate is 0.01 kilograms per second. Part B tells us that the first temperature is 300 Kelvin, and the second temperature is 400 Kelvin, and that the mean velocity is 0.02 meters per second. Now we can list what we were looking to find. Part A asks us to find the following for each fluid: mean velocity, hydrodynamic entry length, and thermal entry length. Part B asks us to find the following for water and engine oil at the two temperatures: the mass flow rate and the hydrodynamic and thermal entry lengths. Here we can see a diagram of our pipe with the fluids flowing through. We can list off our assumptions. First is constant properties, steady state conditions, water is non-compressible, and that the system is ideal, therefore no losses. Next, we will state our general equations. First is our equation for mean velocity. This can be rearranged to find our mass flow rate. Then we have a Reynolds number equal to the internal flow. Then we have a Reynolds number equation for internal flow, our hydrodynamic entry length, and our thermal entry length. I also made a chart of the necessary table values from the back of the book. All of these values can be from tables 5, or tables A, 5, 6, and 7. Now we can solve. So first we want to find our mean velocity for each fluid. We can simplify this equation down to something based on only our density. Then we can solve in parallel for all our fluids by plugging in their respective densities and getting an answer. Up next is the Reynolds number, which has two different equations. Again, we'll solve in parallel for each fluid. We can see which equations were used for each fluid, plug in our variables, and get our answers. Next, we will use that Reynolds number to solve for the hydrodynamic entry length. Again, we can simplify down this equation to be based on only the Reynolds number. So once again, solving in parallel yields our answer in meters. Finally, we can solve for our thermal entry length. This equation simplifies down to the hydrodynamic length times the Prandtl number. Yet again, solving in parallel yields our answer in meters once again. Now we can move on to the second part of the problem. So we're going to rearrange our equation for mean velocity to solve for m dot. Plugging in our constants, and we're going to get an equation based on only each fluid's density once again. And again, we'll solve in parallel. Notice how the mass flow rate of water stays the same no matter the temperature. This is because it's an incompressible fluid and the density stays constant. So the m dot of water at 300 and 400 is equal. Next, we'll again solve for the Reynolds number of each fluid. This time, we need to solve for water at each temperature because the velocity or the fluid viscosity changes. Now we can solve for our hydrodynamic entry lengths for each of the two different temperatures. And finally, we can solve for our thermal entry lengths using the same method as before. Finally, for the ease of comparison, I put all our found values into a table. This is definitely easier to solve using Excel or MATLAB and plugging in equations and variables rather than taking the time to do it all by hand. That's it for this video. Thanks for watching.